people can answer you, or Kishor can answer you after the session. Yeah. So let me take the record.
Yeah, it started, I think. Okay, so let me do the screen sharing.
Sorry, give me a moment. I think I cannot take the recording here.
No, I think it's being recorded, so it's fine.
Oh,
Yeah,
okay, okay, sure.
I can see it. Yeah. Okay. 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 Perfect. Just a moment. I just changed the view to seamless. Yeah. Okay. So yeah, like thanks everyone. Thanks for joining, and thanks Zin for organizing this series. So in general, like I mean, I think in total there will be 18 sessions, and we will discuss starting from basics to advanced level. So we will also discuss things like fault tolerance and uh, various kinds of codes such as LDPC codes, bosonic codes, dynamical codes, approximate codes, and so on. I would appreciate if more people can turn on their camera. So, I mean, it's more human in that sense. But if you can't, that's also fine. So that, like I can see you, like, while like that there are people out there and so on. Okay. Okay, so basically, today I will talk about basically three things. I will start from like very basic like classical repetition code. So there is a classical 3-bit repetition code that will be the starting point. So and then actually all the tools that are needed to understand what is quantum error correction, the analogs of that you can already see in the case of classical 3-bit repetition code. And then we will talk about quantum 3-qubit repetition code. And then we will discuss this stabilizer formalism. So in that sense, today is like, the very basic of quantum error correction that we are going to discuss. So let's try to see what is classical 3-bit repetition code. So as I said, it's a simplest starting point. And since we call it a repetition code, the idea is to encode bits by repeating them. So that's why it's called the repetition code. You repeat bits, and that's how you do the encoding. So let's say here, for example, we talk about like 3-bit repetition code. So here we take a bit 0 and we repeat it 3 times, and that's what we call 0 logical. If we take bit 1 and repeat it 3 times, we call that 1 logical. So those are our code words. If it was, let's say, 4-bit repetition code, then you would have repeated it 4 times, and so on. In that spirit, let's say if it was a n-bit repetition code, then you repeat it, like n times. So that's why it's called a repetition code. You just repeat, and that's how you encode basically bits. So these are your code words: 0 logical, 0 which is 1 0 0 0, and 1 which is 1 1 1. Okay. But why are we doing all this? The idea is that using redundancy, you want to fight error, and errors are bad and they affect your computation. So in the classical case, the error, like that we talk about is bit flip error. So what is a bit flip error? As the name says, the bit flips. So you have 0 and 0 can flip as 1, and you have 1 that can flip as 0. I think there is some like noise in the background. Like please unmute yourself. Please mute yourself. Yeah. Uh, so let's say so yeah, like there was some error in the background. So let's say there was 0 and that can flip as 1, and you have 1 that can flip as 0. So this was a bit flip error. So what we did is that we started with 0 0 0, and then let's say the first bit flipped. So if the first bit flipped, you get 100 because the bit flip happened at the first place. Similarly, for 111, if let's say if the first bit flipped, then you get 011 because 1 was flipped to 0. You start with 000 and let's say second bit flipped, then you get 010. You start with 111 and let's say if the second bit flipped, then you get 101. Okay. If the third bit flips, then you get 001. And similarly here, you will get 110. So these are your code words. Like, that's what happens to your code words after a single bit flip error. So here the bits have flipped, like, just one bit has flipped. And you want to detect that, there is some error, because before you do error correction, you need to figure out that there is indeed some error. And in this case, finding that some error has happened is very simple. You notice that in your code word, all the bits are identical, like it's 000 or 111. On the other hand, the moment a particular bit flips here, for example, here, the bits in the string are not identical. And whenever the bits in the string are not identical, you say that error has occurred. So that's how you do error detection. To do error correction, it's again very simple. You reset all bits to majority value. So for example, let's say 010 is what you get when, let's say, when the second bit has flipped. But then because majority of the bits are still 0, you say that, there is a bit flip here. So it should be reset to 000. So in this way, you do error correction. So you do error detection, and by looking at the bit string, and if they are not all identical, then you know that some error has occurred. And by resetting all bits to majority value, you do error correction. But at this point, somebody could ask, like, what if I start with 000 and then this bit also flips and this bit also flips? So in that case, I get 011. And then if I reset it to majority value, then I will get 111. So that's not correct, right? We started with 000 and we are getting 111. So the error correction is breaking here. And this is breaking here. Why it's breaking here? Because we are assuming that we have an error correction code that works for single bit flip error. But if let's say there is more than one bit flip error, then we are not able to correct. And these ideas are captured by something called code distance. So if you have higher code distance, means you have higher tolerance to error. So code distance basically captures smallest number of bit flips required to transform any two code words into one another. So the case that we are looking at, we have only two code words, 000 and 111. So in this case, it's very simple. You just find the number of bit flips required to go from 000 to 111, and it's just 3. So in this case, your distance is basically 3. If you have n bit repetition code, then in that case, your distance will be equal to n. So let's say if you work with 4-bit repetition code, then the smallest number of bit flips required to transform any two code words into one another will be 4. So that's how, like you look at code distance. I mean, here it's very simple, but in many cases, like you have many code words, and then you try to find smallest number of bit flips required to transform any two code words into one another. So in general, it's a very hard problem. And that's why, like, optimizing for code distance is a difficult task. So at least here it's clear, right? I mean, what is code distance? So you just look for smallest number of bit flips required to transform any two code words into one another. So actually, to understand code distance, there is this object called Hamming distance that can be useful. So the Hamming distance is defined for strings. So let's say I have been given a string A and I have been given a string B, and the Hamming distance is minimum number of bit flips to transform bit string A to bit string B. So let's say I have, like some string, let's say 001. Another string that I have is, let's say 011. Now Hamming distance between here A and B will be basically 1. You just, you know, like you just flip 0 to 1 and you go from A to B. So Hamming distance is just 1. So what you are doing for code distance is that for and and then you are taking the minimum of all. So you are doing, basically you are taking the minimum of all to calculate the code distance. So all possible Hamming distances and the minimum of that basically gives you the code distance. Okay. So code distance basically determines uh like, sorry, like, can I request people to, like mute themselves so that, like there is no yeah, like Zin, like maybe if you could,
Yeah, of course.
yeah. So so basically code distance determines the maximum number of errors which can be detected, uh, which is, like d minus 1. The maximum number of errors, like that can be corrected is actually d minus 1 by 2 floor of that. Now this is also very easy to say because I mean, at least in the repetition code, if all the bit strings are identical, like all the bits in the bit string are identical, then you say that, like no errors occurred. So like, I mean, let's say if the number of bit flips are, let's say, d minus 1, and if the distance of the code is d, then you find that, like all the bits are not identical, and hence you detect the error. On the other hand, for majority, where, like, majority method to work, you need to have, like number of bit flips restricted to the floor of d minus 1 by 2. So this gives you an intuition like why, like the code distance determines the number of errors which can be detected and number of errors that can be corrected. Now you notice that as I increase my distance d, it also helps me increase the number of errors that can be detected, and it also helps me increase the maximum number of errors that can be corrected. And that's why code distance is a, like, I mean, it's good to have high code distance. Then you have, like higher tolerance for error. Okay. So we started with, like, let's say, k bits, and let's say we encode them using n bits. And if the distance is d, then you write it as nkd. Like this is the notation people use. So let's say if you use n, this is the number of bits in your code word. If you use that to encode, let's say, k bits, which is number of bits in your number of encoded bits, and if the d is the distance, then you write it as nkd. So for example, for n bit repetition code, it is n1n, and for 3-bit repetition code, it is 313, and so on. Okay. So we talked about, like this notion of distance also. We talked about error detection. We talked about error correction. So far, we have not talked any quantum. And like there's nothing about quantum, nothing quantum that we have discussed so far. But a basic idea of error correction, I believe you already got. Now you have done encoding, but I mean that's not all. You want to do some computation on the encoded information. So for example, you had 000, which is 0 logical, and then you had 111, which was 1 logical. And suppose you want to go from 0 logical to 1 logical, like you can apply this logical NOT gate. So the NOT gate basically, like its action is same as the NOT gate, which is in the regular setting. So in a regular case, the NOT gate takes you 0 to 1. Here, the NOT gate, the encoded NOT gate will take 000 to 111 and 111 to 000. Okay. So that's what, like the logical operation on the code means. So I think that completes basically the first part, which was about classical 3-bit repetition code. Uh, Next, we will, like talk about its quantum analog, which is quantum 3-qubit repetition code. So far, I think you got like some sense of what is error correction without talking anything about quantum. Okay. So let's talk about like similar to the classical case. Let's talk about this thing called code words. So we had like this zero logical, which was 000. I mean, in the classical case. In the quantum case, you just put a ket around it. Like, so your zero logical is ket 000, which is nothing but like 0 tensor 0 tensor 0. So that's your zero logical. The one logical is basically 1 tensor 1 tensor 1. So you're doing the same as like the classical repetition code. You are just repeating and using that to encode. So that's your zero logical and one logical. But in quantum case, what happens that we have superposition of like this 0 and 1 state. So you have psi, which is alpha 0 plus beta 1, and its encoding will be alpha 000 plus beta 111. So that's what the encoding of a general state alpha 0 plus beta 1 looks like in the quantum case. And basically the span of this 0 logical and 1 logical, that's what you can call the code space. So that's your code space. So it's a part of the Hilbert space, which you can call as error-free encoding of a quantum state. And that's where the error-free encoding of a quantum state lives. And what happens that any error that happens, it takes you out of the code space. And then your job as error correction researcher, or let's say when you are doing error correction, writing a protocol, is to bring back that corrupted state inside the code space. And when you bring back, like you should not end up applying some, logical operation, like, like similar to the classical case. Like, you should not like, bring it back and in the process, like end up doing some unintended logical operation. So you should bring it back to the code space, but you should bring it back, in a manner that that is sensible. Okay, so similar to the classical case, we could see what was the code words, and we saw this, like code space. Now there is this notion of error. Now here we depart slightly from the classical case. So earlier you had bit flip error, which was 0 going to 1 and 1 going to 0, which is action of the X operator here. But you also have a phase flip error, so which acts like 0 going to 0, but 1 going to -1. So let's say if we have some state, like alpha 0 plus beta 1, it will under phase flip, it will go like alpha 0 minus beta 1. So that's under phase flip. Under bit flip, it will go like alpha 1 plus beta 0. And there is this point that, if you can correct, I mean, you want us to show it, but let's say if you can correct both X and Z errors, then more general errors can be corrected as well. So we just care for, like just X and Z errors, and those errors are, like in some sense are like sufficient to correct more general errors. Okay, so you start with alpha 000 plus beta 111. So that's your encoded qubit. Now let's say second bit goes through bit flip error, like second qubit. So in that case, it's same as applying I tensor X tensor I. And then in that case, you have alpha 010 plus beta 101. So this flips here, like this flips here. So that's how, like it looks like. Okay. So we looked at, like what is the meaning of the code word, what is the meaning of error, what is the meaning of encoded state after a single, like qubit flip error, and these are all like similar to what we had in the classical case. I mean, we saw that in case of errors, there is like more general phase flip error, which was not present in the classical case. So there's obviously some depart, but idea is similar. Now for error detection, also it's a bit different. Like in the classical case, we were saying that you just look at the bits, and that's basically one can say is measurement. But in quantum case, you should not measure individual bits in the computational basis, because you can, in fact, you can do that and it would detect the error, but it would also result in the collapse of the encoded qubit. So when you make that measurement, I mean, uh, you figure out that some error has occurred, for example, here, but that will also collapse the information, and we don't want to do that. So this is a challenge, and to get around that, what you do is that you measure symmetries of the state rather than individual bits. So do not measure individual bits, measure symmetries. So one such example is this parity of any pair of bits. So let's say 0, 0 and 1, 1, that has even parity. 0, 1 and 1, 0, that has odd parity. So you measure that, and that can help you figure out which qubit went through, for example, bit flip error. So this is a circuit, like, which is made up, like auxiliary qubit and some CNOT gates, which is equivalent to measuring Z tensor Z on first two qubits. And actually, if you measure Z tensor Z, it has similar effects as, like parity, measuring parity. So for example, let's say 0, 0 and 1, 1, under action of Z tensor Z, there is no minus sign. It's like plus one in front of it. But for 0, 1 and 1, 0, you get a phase, like you get a minus phase. So Z tensor Z helps you figure out whether it's even parity or whether it's odd parity. And notice that this is actually very powerful, because let's say if the error happens on the first qubit, then in that case, Z tensor Z on first two qubit will give you -1. First and last qubit will give you -1. On the other hand, second and third qubit, it will give you +1. Why? Because in both cases, at least, like first qubit is involved, like, so here first qubit is involved, here also first qubit is involved, but here first qubit is not involved. There is identity. Actually, if your error operators anti-commutes it, like, so here it is the error operator. So if your error operator anti-commutes with the operators here, then you get -1. If it commutes, then you get +1. And by looking at this -1 +1 pattern, you can figure out which qubit went through an error. So for example, you get -1 here and +1. So there are three possibilities, right? I mean, if you get everything +1, then life is good. Like, there is no error. But let's say you get -1 here, then first qubit went through error. If you get -1 here, then second qubit went through error. And if you get these two -1, then third qubit went through error. Actually, like this pattern you get is what people call syndrome. It's like that helps you figure out what was the, what's the issue, like which qubit is going through, which qubit is problematic, and what is the problem. So the syndromes help you detect errors, and also, like through something called decoding, also they help you correct errors. Okay. So this is how you detect errors. And error correction in this case is very simple. Let's say the error is XII. I mean, for the 3-qubit repetition code, it's very simple. So if the error is XII, the correction operator is just you apply, like just the same operator. And the reason is simple, like because polys are self-inverse. So if you XII, like XII, that will be basically, like III. So, I mean, that helps us see why just applying the same operator, like helps. So that's how we do error correction. Now, similar to the classical case, as we said, you need to perform operation on the encoded qubits. And for that, you need logical operators. So for example, you need, like X logical operator and Z logical operator. And their action should be same as what we get in the physical case. So you have 0 logical is like, one should go to 1 logical under X. 1 should go to 0. Under the action of Z, 0 should go to 0, but 1 should pick up phase. So one possible choice of such X operator is, XXX, because we had, in our encoding, we had alpha 0, 0, 0 plus beta 1, 1, 1. Now let's say if we act with XXX, then it will become alpha 1, 1, 1 plus beta 0, 0, 0. So you see that, I mean, it's like acting through X in the unencoded case here. And for Z, one such choice is ZII, like so that can induce a phase, and that works. One can ask, like, why are we saying one possible choice of X and Z? Yeah, this is because there are many choices exist, and actually using the stabilizer formalism, you can figure out what are the different choices for logical X and logical Z. Now, finally, you need to talk about this thing called distance of a quantum code. And for that, we need to understand this object called weight of an operator. So weight of an operator is number of qubit it acts non-trivially on. So let's say you have xii, its weight is 1. You have ixi, its weight is 1. Because its identity at two places, but here it's like a non-identity object. xxi, its weight is 2. zii, its weight is 1. If you have zzz, its weight is 3. So here the weight is 3. Now, distance of a quantum code is minimal weight of any non-identity encoded logical operator on the code. So basically, and it makes sense, right? Because in the classical case, it was a number of bit flips required to transform one code word into another, like the minimum number of bit flips. And how do you go from one code word to another, like through some logical operation? And so that's why you look at, so there, since we were just talking about, bit flips and all, I mean, everything was formulated in terms of bit flips, but now here, you can have like, X, Y, Z, and so on. So you ask for what is the minimal weight of, a non-identity encoded logical operator on the code, because at those many places, X, Y, or Z can occur, and that will take you from one code word to another. So that's so in that sense, it's the analog of distance of a classical code. Okay. So distance of a quantum code is minimal weight of any non-identity encoded logical operator on the code. So you look at all possible, encoded logical operators, and then you look for the minimal weight logical operator, and that the weight of the minimal weight logical operator gives you distance of the quantum code. So here, basically, the distance is, for X, the distance is 3. You can figure out. The distance for Z was 1. And as we saw earlier, if the distance is, let's say, D, then you can detect D minus 1 error, correct D minus 1 by 2 floor of that. So if you put D equal to 3 here, then for X errors, you can detect 2X errors, like this 3-qubit repetition code. And you can correct 3 minus 1 by 2 floor of that, which is 1. So 1 qubit errors you can correct. But in terms of Z, you cannot even correct 1 Z error, because the dz, the distance for the Z case, is like 1, and 1 minus 1 is 0. So D minus 1 is actually 0, like for the Z case. So the quantum 3-qubit repetition code can detect 2X errors and no Z errors. And you see the reason now. So basically, actually, when we talk about distance, we look at the minimum of the X and Z distance, and that's what we call distance of a quantum code. So far, I mean, we talked about classical 3-bit repetition code, and then we talked about quantum 3-qubit repetition code, and you saw that all the ideas which are there in the classical case, similar ideas exist in the quantum case, and there is not much difference. I mean there is some difference at fundamental level, but there is a parallel between the two. And to understand this, the quantum codes, there exist many formalism, but one of the most popular formalism to understand quantum codes is this thing called stabilizer formalism. So the remaining part of the tutorial today, like next 20 minutes, 30 minutes, whatever, I will just discuss stabilizer formalism. And I hope that gives you a brief, understanding of, quantum error correction. So we talked about classical error correction. We talked about quantum 3-qubit repetition code, which was similar to classical 3-bit repetition code. And now we are talking about a formalism that helps us understand at a bigger, gives a bigger picture. Okay, so let's try to understand stabilizer formalism. So most error correcting codes, actually they can be studied via stabilizer formalism. And many codes that you might have seen, the Shore code, Steen code, 5-qubit code, all CSS code, story code. Actually, story code we will look at in the next session. Planar surface code and so on. You can study them through stabilizer formalism. It's a widely used formalism to describe topological codes. So, that's why it's useful. And we will see how we can use it to derive encoded logical operators. So it's a very, I would say, powerful formalism. So stabilizer code is basically a quantum error correct. It's a kind of a tautological definition. There is a better definition that you can find in the book by Daniel Gottsman. Yeah, here is kind of a tautological. It's a code that can be defined in the stabilizer formalism. So there is a stabilizer formalism using which you can define the code. But yeah, it helps. So these stabilizer codes, they are defined by specifying. Actually, it's incorrect here. Or maybe overcorrect. It's just a moment. So they are defined by defining a stabilizer generator. You don't need these encoded logical operators. So by stabilizer generators, you can define a group called a stabilizer group, and they help you define a subspace which remains stable under the action of the elements of that group, and that's what help us define the code space and then other things similar to the previous case. So let us say, we have some bunch of, code states. Like let's say we have some code word basis state, let's say size a bunch of code word basis states. So stabilizer group is basically, it's a subset of poly group. So you can call it a set of poly operators which leave all code word basis state size invariant. So let's say you have a stabilizer group S. Let's say stabilizer group S. So this should be S here. So for all polys which are in S, when you act it on size A, which are in your code space, it should remain, stable. So PK on size A should give you size A. So this is what we demand. So a stabilizer group is a set of poly operators which leave all code word basis states invariant. And any stabilizer operator or stabilizer element is a member of the stabilizer group. So any S which belongs to this capital S group, we call that, stabilizer operator. Now you notice that, it's very easy to see that the set of stabilizer operators must commute. It's very easy to see because, we are working with the stabilizer operators. They are poly, and the poly either commute or they anti-commute. So let's say we have two stabilizers, let's say, call them, let's say, I don't know, P1 and P2. And let's assume that, they are P1 and P2, they belongs to S, but P1, P2 don't commute. So P1, P2 is minus P2, P1. Because if they don't commute, then they anti-commute. But because they are in a stabilizer group, P1, P2 psi for any psi in the code space should give you P1 psi, because P2 psi will be psi because P2 is a stabilizer, and then P1 psi should give you psi. So P1, P2 psi should give you psi. But then when you do minus P2, P1 psi, that will give you minus P2 psi, and that is minus psi. So if you, if you use 1, 2, and 3, that gives you a contradiction because 1 is equal to minus 1. That cannot happen. So we arrive at a contradiction. So P1, P2 should be equal to plus P2, P1. Okay. So all the stabilizers, stabilizer operators, which are in the stabilizer group, they must commute. So it's a very easy proof here. So any group G, like in general, can be specified by a set of generators. That helps you get a succinct representation. But when you are working with an abelian group of self-inverse operators, let's say in the case of stabilizers, any element G can be written as Gj alpha j, where alpha j is 0 and 1. So that helps us see that that the size of such a group G will be 2 to the power m, because that's set of all possible bit strings that you can get, like it's like 0 0 0 1 1 1 and so on. So the size of such a group is 2 to the power m. Now that's very useful, because let's say you start with like n qubit, then the size of the Hilbert space is 2 to the power n. And every stabilizer basically partitions your Hilbert space in two parts, because they are polished. So either they can be in the +1 subspace, or your quantum state can be in the -1 subspace. So you basically partition it, yeah. And if you have, let's say, m such stabilizers, then the total number of partitions that you get is like 2 to the power m, and that's basically size of the space where you have your code state lives in. So that's like if you have k quantum states, sorry, so if you have k qubit quantum states, so that 2 to the power k. So basically you have 2 to the power n by 2 to the power m is equal to 2 to the power k. So from here you get n is equal to m plus k, or like m is equal to n minus k. So this is very useful. Like this tells you that if you have k logical qubits, n physical qubits, and m stabilizer generators, then this is the relation they have to satisfy. So if you increase your stabilizer generators, then, and if you keep your n fixed, then k has to go down. On the other hand, you also see something interesting, is that number of stabilizer generators, like m, scales linearly with n. Yeah. Okay. So this is good, like this n equal to m plus k relation. So let's apply to 3 qubit repetition code. So in 3 qubit repetition code, our n was 3, k was 1. So m was basically 3 minus 1, that is 2. So order of the stabilizer group, as you see here, was 2 to the power m. So that's 2 to the power 2 here, that is 4. So we had the ZZI, ZIZ, IZZ, and III. These are in our stabilizer group for 3 qubit repetition code. Okay, so we could see so far, like just as a repetition, that what is the meaning of a stabilizer group, and then we saw a stabilizer operator as an element, like a element of the stabilizer group, and then we saw that the set of a stabilizer operator, they must commute, because if they anti-commute, then we have some contradiction. And then we said that any group Z you can specify by a set of generators, and in our stabilizer case, because we're working with abelian group of self-inverse inverse operators, uh, the size of, let's say, if you have m generator, then the size of group will be 2 to the power m. And from there we said that if you have, let's say, n qubits, then the size of the Hilbert space is 2 to the power n, and size of your stabilizer group is 2 to the power m, and like the ratio of these two gives you size of your code space, and that basically gives you the relation that n equal to m plus k. Okay, so m is equal to n minus k from here, you can say. And then we looked at the 3 qubit repetition code, where we took n equal to 3, k equal to 1, and that gave us m equal to 2. And then you can specifically write what are the elements of the stabilizer group. So we had our code states look like alpha 0 0 0 plus beta 1 1 1, and you can in fact check that under the action of these operators, our code states, like they remain stable, like you get +1. Okay, so we talked about, like what is the meaning of code vectors, code states here, and then we talked about, the generator, stabilizer generator. Now, how to do error detection in the stabilizer formalism? So you can detect errors by measuring the stabilizer operators. Now, again, if you directly measure, that's a problem. So you using some auxiliary registers, you measure it. And suppose you want to measure P1 tensor, P2 tensor, P3, this is how you measure it. So this is the circuit. Now, M measurements actually suffice. So these M measurements correspond to, like a stabilizer generators. So you just measure the operator which correspond to stabilizer generator. And because M is N minus K, so M scales linearly with number of physical qubits. So you don't need to measure, like too many operators. And once you measure, you get a bunch of bit strings. And those bit strings is what you call syndrome. So syndrome is outcome of the measurement of a given stabilizer generator. So that's a syndrome. So syndrome is like, you can think of, it's like suppose you have some illness or something, and then it's a test report that you get. And based on that, like you figure out that, like, oh, some disease has happened or so on. So where the disease happened, what is the disease and so on. All that you can figure out by looking at the syndrome. Okay. So syndromes help you, like detect the error. Yeah. Okay. So, okay, fine. So basically, we look at, like error detection and the error detection circuits. Now, encoded logical operator in the stabilizer formalism is also easy to see. So let's say we had 0 logical was 0, 0, 0, 1 logical was 1, 1, 1 for 3-qubit repetition code. And our code state was alpha 0 plus beta 1, which was alpha 0, 0, 0 plus beta 1, 1, 1 when we encoded it. Our X was X bar, like X logical was X, 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 Z logical was Z, I. But instead of Z, I, one could have used I, Z, I and I, Z also. And one could ask, can one characterize, like the equivalent set of logical operator, all logical operators which are, like possible and so on. And actually a stabilizer formalism helps you precisely do that. So notice that, like let's say psi is some state in the code space, and let's say L is some logical operator. So because psi is a state in the code space, and let's say Sj is some stabilizer, so under the action of Sj, psi should remain psi. So if you do LSJ psi, that is same as doing L psi. So it tells you that the action of LSJ and L is actually same. So, basically, for every logical operator L, there exists a family of 2 to the power m logical operators, LSJ, like this set, like, so you all possible SJs, like, that act equivalently on the code space. So that tells you, like which logical operators are equivalent. So basically, so there is this claim that a logical operator must belong to the centralizer of the stabilizer group. That is correct, but like actually one should say centralizer, but not in the stabilizer. So it should be in the centralizer, but it should not be in the stabilizer. It should not be there. So why do we, like, what do we mean by centralizer? It's basically set of operators. So let's say, like, here is, I just added the definition of centralizer. So let's say you have some, like some element Z of a group G. A centralizer is basically all those elements of this group G which commute with Z. So, like all those X in G such that XZ equal to ZX. And you can actually elevate this definition to some subgroup H of the group G, which is all those X in G which commutes with all small h in capital H. So that you call, like centralizer of the group. So we have this group, we have this poly group, and then we have this stabilizer group, which is a subset of the poly group. And you look at centralizer of the stabilizer, but those but like those operator, they should be in the centralizer, but they should not be in the stabilizer. If that is the case, then then you call it a logical poly operator. And actually this definition, it makes sense because the action of the logical operator should be, like move the code words around. It should not take you outside the code space. So they should be in the centralizer. But, every stabilizer will be trivially in the centralizer. So we don't want, a logical operator to be a trivial logical operator, like, just that stabilizer. So to get rid of that, we look at centralizer of the stabilizer group minus the stabilizer group. And all poly operators which belong there, you call that, like logical poly operator. So I hope, this definition makes sense. And once we have, like characterized, like centralizer, sorry, again, I'm centralizer minus a stabilizer, I should say. So once you have characterized this, this set, then the minimal weight of any operator in this set gives you, the distance of the code. Because as we said earlier, distance of in the quantum case is the minimal weight of any uh, uh, non-identity logical operator. So that's what gives you the distance. And logical operator, because it lives in the centralizer, we look at, like any operator which is in the centralizer, but not in the stabilizer. And we look at its weight, and the minimal weight gives you the distance of the code. So you see that using the stabilizer formalism, we are able to figure out many of these things, like, very easily. Like, the stabilizer formalism help us write these stabilizer generators, and from there which it tells us what should be measured so that we can detect errors. And then it tells us, the encoded logical operators. And then by looking at, like the minimal weight of the encoded logical operator, it gives us the notion of distance also. It also tells us, like which logical operators are equivalent, and so on. So yeah, I think for the 3-qubit repetition code, the stabilizer group that we had was, like this is a stabilizer group, this is the centralizer, and this is how it looks like. For 5-qubit stabilizer code, you can figure out these things yourself. Next week we will talk about, Tori code. So I think this should give some sense of, like what is quantum error correction. I talked about, I think today, 3 things, like classical error correction, like classical 3-bit repetition code, and then quantum 3-qubit repetition code. And then towards the end, like what is the meaning, what is a stabilizer formalism. Some of the things may be, I think, new to people. So I will share the slides, and people can discuss in Discord and so on, and chat. And next week we will try to, discuss Tori code using stabilizer formalism. Yeah, thanks.
Okay, thank you, Kishor. Thank you for your nice talk here. And there are some questions in the chat. If you can, you're free to answer. Or somebody has already answered the
Yeah,
questions.
so yeah, I think there are. Yeah, so I think there are many questions and so on. So I would say I think it's difficult for me to go to one by one.
Yeah.
But I would say people can, like continue with the discussion on the Discord and so on. And yeah, like others can answer and so on. Yeah. So maybe we can stop the recording, and yeah, like I believe it will be put on YouTube also. Yeah.
Okay, maybe you should stop the recording. I cannot do
Ah,
that
okay.
here. Yeah.
Okay. Let me.
So if you have any other questions, just go to the Discord chat.